Hey guys, in this video we'll be looking at NMOS pass transistor logic, and we will be creating an AND gate to explain how it works so that we get a clear understanding of the topic. So talking about the NMOS pass transistor logic, let us take a MOSFET that is given here. The left part of the MOSFET is going to be the input, which is denoted by N in. The control will be done using the gate, which is going to be given to the gate terminal, and then we get the output at the right hand side. So one thing that we have to note here is that as long as the gate is 1, the input will be given to the output. As long as the gate is 0, then irrespective of whatever we give to the input, the output is going to be what was the earlier state, and we usually denote this using high Z in case of Verilog and in VLSI. So the one main thing that we have to note here is that as long as gate is 0, we get an output of ideally 0. So what happens here is that we can realize that we are creating some sort of an AND gate here, where the output is equal to the input dot the gate. So here we can understand this better by looking at an example. Like I said, like we can look at this example that has been given. So initially the top the top transistor is going to be implementing A dot B, which is going to be the final output. So the left side is the input A, and as long as B is equal to 1, it will pass the value of A to the right hand side. So it implements a beautiful AND gate. Like we can see, the MOSFET is going to act as an AND gate. But why do we have the bottom part is a question that should arise in your mind. So let me explain why. The bottom part is called as the auxiliary circuit. So like I said earlier, in the previous slide, we saw that if the gate is 0, or in this case B is 0, we cannot determine the output value of the top transistor definitely. Rather, we will be getting into a state called as the high Z impedance state. The impedance logic would be implemented. Now why is this a problem? I'll tell you why. Because let us say B is 0 and the previous value of the output was 1, you will see that the residual capacitor's charge value will influence the output and will not pass a perfect 0. So what happens is here there is a logic mismatch, and there might be issues later when we are creating complex circuits, and this might even if things go worse, this may even act as inferred latch. So this is why we go for something called as an auxiliary circuit. So the auxiliary circuit will have a gate pulse that is the negation of the gate given to the initial logic. So if we are giving B to the gate of the top transistor, what we will be giving to the auxiliary MOSFET is B bar, so that both of these MOSFETs are not on at the same time. Let us say B is off, which is going to be causing trouble in the top circuit. What will happen is the bottom auxiliary circuit will be on, and since the bottom auxiliary circuit is on, the 0 is passed to the output. Now you can ask, why not implement A and B bar on top and implement 1 and have a auxiliary circuit with the gate pulse as B. The problem with this is that NMOS does not pass a perfect 1. So the NMOS logic only passes a perfect 0. So we use 0 to pass a perfect 0 to the output. So we need something called as an auxiliary circuit, so that we have